to understand the diffuse universe.
Oh, that's sad.
What happened?
That's alright, it's not a big deal. For those of you who are font nerds, this was all supposed to be in OCR, optical character recognition font, because I'm interested in this question of using machines to understand things, but it's not anymore. But luckily you're not machines, so you can read this just fine. In any case, I'm going to be talking to you about trying to understand the diffuse universe. And I think the role of astronomers and astronomy in this context, among this crowd, is to show pretty pictures and to provide hard problems. And so I'm hopefully going to do both of those things. I'm not going to tell you a whole lot in the way of answers. This is very much the beginning of an exploration that I really want your help on. Communities of machine learning, communities that do statistics, communities that interpret large data sets are really going to be useful for, and I just sort of want to pose this problem to you because I think it's a problem that has not been well posed, or at least not commonly well posed. So here's the layout of my talk. First I want to talk about things in space. Then I want to talk about not things in space, space but not the things. I want to talk about a love affair that's gone on for a long time between machines and objects, and how great we are at thinking about objects and how great we've taught machines to think about objects. I want to just give a case study of what I've done a lot of work on myself for my thesis and in my postdoctoral career, studying the neutral hydrogen interstellar medium, which I think poses a very interesting problem in this context. It's not the only version of this problem, but I think it's a good one. Then I want to sort of roll up a couch here and lie down and talk to you about my problems and tell you what they are, what progress we've made. One of this way so I can distribute the poll damage here. And what progress we've made, but really I'm not going to tell you a lot about progress. I'm going to tell you most of the problems. And also in particular from that one work by Destry Saul, who's in the audience here, and then I want to tell you that this problem gets worse. So I hope this is a very optimistic talk.
Is this going to be more pessimistic than the last one?
It's going to be, yeah, we'll take both, yeah, just whether it's more or less pessimistic. Okay, so, I'm also going to show an infinite times fewer equations, and I'm also going to show a very, very small fraction of words. So there's going to be a lot of talking and images, so if you need to read things, you're in trouble. I'm going to start at the very beginning, which is to say with our ancestors looking up in the night sky. And so what was different about the night versus the day? Well, the night was full of these stars. And in particular, the night's really different from the day because during the day you see clouds. You see things floating around. And you'll notice that no clouds have names like Sirius or Rigel or what have you. We reserve those for stars. And it's because every night the same stars come back. And that they're objects, they sit there. And even planets, you have the same, you've got Saturn, you've got Jupiter, but the planet that goes by that looks like a duck doesn't have a name because you're never going to see it again. And it's not even a very well-defined object. So our first intuition about stars, I think, was actually really accurate. And the universe in general was a really good intuition, which is that there are things out there, and they sort of are really well-defined as things. So your star is incredibly well represented as an object. Right? If you and I were stars in the universe, we'd be separated typically by, if I were the size of a star, we'd be separated by about the size of the Earth. The nearest star to me would be on the other side of the Earth. And so that makes us a really, it's very clear that this is a thing and that's a thing and there's nothing in between. And then nothing is really well defined. Density contrast between a star and what's outside the star is sort of order 10 to the 24, 10 to the 26, 10 to the 28. That's a really steep density contrast. And we can determine objects in this room even though their density contrasts aren't so well, and we can name them and so forth. So I think we were really good early on at talking about objects in space. And that psychology has persisted in terms of the way we think about astronomy. But I want to talk to you more about the diffuse universe, not just objects in space. I hope you're all very proud of me. This is my first pie chart. I've never had a pie chart before to talk. I've never made a pie chart before. Really exciting. Anyway, so this is the universe's mass energy budget here. And a thing I just sort of want to point out is how diffuse, when you actually look at what's going on in the universe, things really are. So the gray there is dark energy that was spoken out earlier today. And that's obviously very diffuse. It's even very psychologically diffuse. It's not really clear we know what we're talking about. But it's 73% of what we would call the mass energy budget of the universe. Then there's dark matter. And dark matter is these tiny, weakly interacting massive particles that are flying around through this room, through everywhere at all times, and they're certainly rather diffuse. Now, people, when they talk about dark matter, talk about it in terms of quotes halos, which are in some sense objects, but we know, and I'll show you in some later slides, that there's a lot of diffuse stuff going on with that too. But even if we just talk about the atoms, the baryons, as we were talking about before, let's see, 7/8 of that is gas. Okay, this is just hot gas that permeates the universe, that's clustered around galaxies, but certainly isn't in objects in any sense. So even if you just talk about the atoms, we're mostly talking about things that aren't objects. And this wasn't apparent to us, when we were ancient people lying on the beach looking at the stars. We weren't, this much of it we really didn't see. And indeed, actually, most of this we don't see either. But there's a tiny sliver of this that we see, and that what we see is really, really quite compact. But when we're interested in the universe, a lot of it's diffuse. Now, I feel like I'm kind of selling you a line here, because I don't think that we need to be interested in this stuff equally by unit mass energy. For instance, I'm terribly uninterested in the 73%. This is, as far as I can tell, two numbers, and at some point, maybe somebody like you will tell me reasons to be very excited about this, but for now, I'm terribly bored by it. So I don't think this is a terribly good argument for what you should be interested in. This might be a somewhat better argument for what you should be interested in. This is a different budget than the 2012 astrophysics budget. Now, I'm not quite dumb enough to get into a political discussion about the astrophysics budget of NASA in this building. That's insanity. But I do want to point out what the biggest wedge of the pie is right now. The biggest wedge of the pie is cosmic origins. Now, this is sort of a broad gloss for all sorts of different kinds of projects that are happening within NASA. But the thing about origins, when we're talking about the universe, is that everything started off really diffuse and became really dense. You can sort of tell the entire history of the universe by just saying, we started off as a big diffuse thing, and then we became a dense thing via gravity. That's kind of, if you just wanted to say astronomy origins in one sentence, that's what you'd say. And so I think cosmic origins, the idea that we are, as a group, interested in, as represented by this, as a group, we're interested in the origins of various things we see. That means we need to be understanding the diffuse phase. We need to understand the diffuse universe as well as these point-like particles, stars, planets, and even galaxies, which I'll get to. So to go to the beginning again, this is the WMAP sky, again, prefaced earlier. And what you're seeing, what you're looking at, is a giant diffuse gas. You're looking at the universe a couple 100,000 years into its evolution, and there aren't any objects formed. This is how we started. It's this big, hot gas that's very diffuse and is the entire universe. So this is very much our origins, and is very much can't be classified as an object. Now, cosmologists have gotten very good at developing algorithms, ways of thinking about this object in particular, well, this not object in particular, and all of these decompositions that you saw earlier today, I think, speak to how well cosmologists have solved this particular problem. And I guess I'm going to stress throughout this talk how bad we are at doing this for the rest of the diffuse universe. This is the Millennium simulation, and again, what you're seeing here is dark matter. So this is all the dark matter in a simulation, a gigantic simulation of the evolution of the universe. And you can see that indeed there are kind of point-like things that you might consider objects, but they're connected in an incredibly intricate way. If you thought about this just in terms of points, in terms of halos or locations or something, you'd be missing a lot of the information. Why do these filaments work the way they do? How are they connected? How well can we probe that into the universe? So there's a lot of diffuse information here that, again, does not look like the night sky. This is a simulation by Greg Bryan and friends of the formation of a cluster of galaxies. And what you're seeing in red is gas. Gas flowing along cosmic filaments and flowing into galaxies. And this, I think, is demonstrating rather clearly that you really do need to understand the diffuse phase if you want to understand how something as large as a galaxy forms. So I'm going at the smaller and smaller scales here. So here, you're not only seeing the formation of this entire cluster of galaxies, but individual galaxies. And as that gas flows in, this is something that Columbia Astronomy is specialist in both through observation and through simulation. So I think, again, now we're getting down to the galaxy scale, and it's important to understand these kinds of phenomena. This is astroporn. This is the Carina Nebula. Really beautiful image. You've got Eta Carina over here, the largest star in the galaxy. And you can again look at the points in this image, and they are telling you something. They're telling you where the stars are clustered, they're telling you where the bright stars are versus the dim stars. But there's tons and tons of information in this image that we don't really understand how to process in a machine way. You can again say, this cloud looks like a duck, and that cloud looks like a duck, and then you can write a paper about ducks. But that wouldn't be, that's not the way we think about interpreting data in a modern context. So how do we take all this information in that's just coming off telescopes incredibly quickly, and try to say something about it that tells us something about the way the universe is constructed? Okay. Zooming in a bit, this is now talking about the formation of stars at the smallest level. So I've actually just this little spot here. And what you're seeing is a star being formed inside a dense column of that dust and gas we were just talking about, shooting out jets as the star forms, and that stuff interacting with interstellar medium. And I think the thing to stress here is that there's morphological information here. There's information that's embedded in this gas, embedded in these images, that isn't just about the spectroscopy. It's not just about how many stars there are or where they are. It's not just about it's really encompasses a lot of shape information. So these things are called Herbig-Haro objects, Bauschocks. And that's the sort of thing that we want to be able to say. How many of those are there? Where are they? And that's I think a big challenge. And now zooming in even closer, you're looking at a single star here with the jet coming out of it, and what you're seeing here, this darker area is a disk of very dusty gas, which is where planets form. So now we're getting all the way down to the Earth scale, if you will, where we're forming planets, and again, there's all this sort of interesting information there. So again, now I want to document this love affair between machines and objects. Machines as our, how you'd say it, our mental progeny or something, have the same affinities we do. And they're really, really good at interpreting objects. And I think there's been a lot of great work that I want to sort of emphasize as to how good we've been at this. So Sloan has come up, Sloan Digital Sky Survey has come up a few times, and it's, I think, in some sense, this industrialization of taking data is the reason it's given us this huge flood of data to run new algorithms on. This is a hero of mine, Jim Gunn, and the camera. This is the camera for Sloan. And the way Sloan works is to take huge swaths of data at a time. It basically just drifts across the sky, taking data as it goes. This is revolutionary because it was able to take a huge amount of data in a very consistent way, so that it could all be processed by machine. That's the telescope, and this is what the sky footprint looks like. And so what Sloan does, though, is it's not interested in this. And this is a beautiful image, but it, nobody wants the output of Sloan to be an image that's, I don't know exactly if I could do this off the top of my head, but a couple of tens of millions of pixels on the side, and somebody hands that to you, and you say, "Great, now I have a picture of the sky," which is what I always wanted. No, that's not what you want. What you want to know is something about the stars themselves. How do these stars populate some kind of diagram? What can we know about the distribution of the objects? Right. That's the real output. And so Robert Lupton, among others, put together this thing called the photometric pipeline, which takes in the raw data that comes off this camera and through this telescope, and instead of making this giant image, which again is beautiful, but not terribly relevant, instead gives you information about objects. So the way it works, incredibly roughly speaking, this is a slide stolen from the Psychoder conference given by Mike Leonard. And what it does is it just goes and tracks down individual things that it considers objects, stars, and it tracks them down and it calls them parents. And then any object that might have sub-pieces, it tries to break those up, because it might say, like in this case, you get a star and another star. Maybe there's a galaxy in here, some other stars, and it wants to, assign the flux to the correct object. And then it takes all of those objects and it figures out all sorts of information about it. So you should clearly read every word on this slide. What kind of object is it? How bright is it in different bands? What's the chance of this thing being a cosmic ray strike or being some kind of glitch? What's the quality, et cetera, et cetera. So that's what's really, this is what's actually coming out of it. And these are the objects that we've designed computers, object-oriented programming and so forth, to use that gloss. That's what we're trying to get at, is the information, so that we can plot X versus Y and see, oh, look, there's a color magnitude diagram, or whatever it is you're interested in, as an ensemble of objects. This is work by Andrew West, who did a lot of work trying to reconstruct large galaxies out of the photometric pipeline from Sloan, and this is a known problem, but he sort of posed the problem very well of showing that if you have a galaxy here, so this is a nearby known large galaxy, the photo pipeline through a process called deblending will take it apart into all these little objects. So it doesn't like the idea that objects are extended. It tries, it knows the galaxies have some size that are just points, but it can't, we're not designed around this kind of principle. That makes sense. We only have a few nearby large galaxies, so we would never design the pipeline to handle this kind of thing. And so Andrew's work was, part of his work is to go back and reconstruct these things and see what Sloan sees for these bigger galaxies. But I think this is this points to how we're not in a mindset, or our code is not in a mindset, for trying to understand these kinds of objects. Another great triumph, I think, in astronomy and in instrumentation is the National Virtual Observatory. And I'm by no means a pro on this at all whatsoever, but the Virtual Observatory is this idea that we can design a set of tools that are very broad, that can allow us to take all sorts of different data sets, collate them together, and talk about how do they work together. Kind of now that I have the brightnesses of these stars, say from Sloan, what do they look like in the UV? What do they look like in the radio? How do they vary in time? Those kinds of things. But it's very much oriented around the idea of objects. When you ask for a region of sky, it will serve you back every object that's found in some overlapping set of databases. And there are images, some image of the sky here, but it's very much oriented around this object-oriented way of thinking about astronomy. But very, very amazing for being able to collate all this different kind of information together. And then, of course, I wanted to put in a little shout out to astrometry.net. This is Hogg's child, I don't know what you call it, but anyways, it's an amazing device. And basically what it is it takes in images like this and tells you exactly where you're looking. So what it can do is recognize all these points, call them all objects, then go back through a database of known stars, take that and figure out the registration, where exactly you're looking, which is a huge annoying problem in astronomy. And basically he and Dick Brinkmeyer, I guess, decided that it was a stupid problem and nobody should ever have to solve it again. So they just wrote, along with a lot of very smart graduate students and postdocs, this algorithm for doing it. But again, it is designed entirely around this idea that we have points in space. That we have these little Gaussian points, they all have values of various kinds, and that this database is an organization of those objects. Okay, so now I want to talk about the neutral interstellar medium. So I did a lot of my thesis work on studying gas, neutral gas in our galaxy. Okay, so this is a view of NGC 628 from the Things survey, and this is a different galaxy. This isn't, of course, the Milky Way, and this is what it looks like in the optical-ish. And here's what it looks like in the neutral hydrogen. So you can see that the disk is very extended. You can see all these beautiful spiral features in it. And this gas is important to understand because it's part of a relationship with the formation of stars. So a bunch of stars kicking around your galaxy, some of them die, they kick material back out into the galaxy, that material cools, becomes this neutral gas, then it forms under gravity into molecular clouds, becomes stars again, and there's this recycling process that many of you are probably familiar with. So understanding the structure of this gas is crucial to understanding how stars form and what the structure of our galaxy really is. So if you're looking at NGC 628 from where you sit, it kind of looks like a thing. There's nothing over here, there's nothing over here, there's nothing over here, and then there's a thing in the middle. Now it's not as thing-like, it's not as object-like as a star, which is really a point in the middle of nowhere. But if you look, if you pointed your telescope over here, you really wouldn't see anything. So at least it's a contained object. Well, that problem, that simplicity goes away when you're talking about our galaxy. So what I'm showing here is the Leiden, Argentina Bond survey. So this is a survey conducted in neutral hydrogen, 21 centimeter line neutral hydrogen, of the whole sky. And you can see that there is data in the whole sky. It's a full sky covering image. This is a Utah projection. So this is galactic north, this is galactic south, and this is the plane of our galaxy. Now I'm showing it crushed. Now when you look in any given direction in the sky with the radio telescope, you're going to see a spectrum, right? So this isn't actually an image, the data set that this Leiden Argentina Bond survey is, it's actually a data cube. So you get a position, say galactic latitude, galactic longitude, and then velocity as your third dimension. Okay. So that's the kind of objects I'm going to be talking about over the course of the next little while. is these PPV cubes, position velocity cubes. So we are trying to, a lot of my thesis work and work that I've been doing with Destry has been trying to expand this kind of effort. So instead of doing this with a 25-meter telescope, we're doing this with a 300-meter telescope. This is the Arecibo 305-meter telescope, the largest telescope in the world. Don't let anyone ever tell you otherwise. This is the alpha receiver. So this thing is a 7-beam focal plane array. And the idea is that instead of, so up until 2004, basically the telescope would look in one direction at a time. So, you talk about your megapixel camera, your gigapixel camera. We had we had a single pixel camera for a long time, and now we have 7 pixels. So we're able to explore the sky 7 times faster, which means making maps of the sky makes a lot of sense. It didn't really used to make any sense. And what we've added to this is our own custom-built spectrometer that can take 8,000 channels of data simultaneously for 2 polarizations over 7 beams. So this thing is able to scan the sky quite quickly and take integration every second. So what I'm going to show you is some of these data cubes.
How big are your pixels, Josh?
So the typical scale of our full image is going to be sort of thousands of Nyquist pixels by thousands of Nyquist pixels by 8,000 channels. So that's the kind of scale of the final data product. So I'll just show this one again. What we're doing is scanning through in velocity. Okay. Now color here, I've just taken. I'm basically just scanning 3 colors through the data cube. So there's red, green, blue, and I'm just scanning them through, which allows you to see these structures. And the edges that you're seeing are just areas we haven't surveyed just yet. So you can see.
So what fraction of the sky is this?
When we're done, we'll be about 35% of the sky.
That's cool. And on this
Yeah.
plot, so we're looking at 100 degrees across?
This is dozens of degrees is the typical scale. So this is like 2 dozen degrees or something, a couple dozen degrees. So each channel is 180 meters per second wide, and then the typical resolution is a milliradian. Just give me sort of thousandfold. So what I'm trying to emphasize here is it's very hard to interpret this data. I'd be very happy if anyone could tell me anything about what they just saw. Not just people in this audience, but anywhere in the world.
It's dynamic.
Yes, as far as I can tell, nobody has any idea what's going on here, including me, and I made these data, so I don't really, that tells you something. I really want to understand better how to look at these kinds of data, because we've got a lot of it, and there's a lot more coming. Okay, so I'll just walk through these a few more times.
Put it on YouTube.
Yeah, for instance. So I want to talk about a couple ways that astronomers have tried to interpret these kinds of data in the past. And I think about this in sort of 2 methods right now, neither one of which I really like. This is the observer's method. So this is work by Naomi Griffiths and a company. These are the Australians are really interested in this kind of work, and that's what she is. And what this is called galactic supershell number something or other. So what you're seeing here in black is a place where there is gas, and then you're seeing a place where there is gas. Notice the galactic latitude here is labeled in degrees. So this is this is the plane of the galaxy, and this is just a couple degrees off. This is from a survey that's just focused on the plane of the galaxy, not the whole sky. And what you see is there's a big hole in the middle. And this is a hole at 36.28 kilometers per second. So as you scan through in velocity, you can, you'll see different features as you go. But it's not completely clear that places in velocity, this is not a position cube. It's a position velocity cube. And so it's not completely clear to me that we really understand how to do this, how to go from this position velocity space into a space that we know how to deal with. And so when you see a hole like this, you might think, well, a supernova went off, that blew material out, and we've got these chimneys, and, you can tell a story about this, but we don't know how to find these things in an automated way, and we don't really know what they mean yet. So this is sort of my, here's a duck, I'm going to write a paper about ducks kind of situation. And I think that's very important, but again, there's no way to statistically quantify this kind of thing, and again, I don't really know if we know what we're looking at. So this is a paper I was involved with that does the completely opposite direction. So instead of the observer's method, this is a theorist's method. So this is work by Alexei Shepardov from about 2005 to 2010. And the idea is the following. So you make an assumption. You say, well, look, I'm looking in one direction, and for a given pixel, I'm going to be seeing in this structure of gas some turbulent eddies. Okay, so when theorists talk about the interstellar medium, they're typically talking about how turbulence works. How does this thing evolve and eddy. And as this beam gets bigger, if you average your beam larger and larger, you're going to see a different spectrum. And that spectrum will get sort of blobbier and blobbier because you'll be resolving larger and larger eddies, and you'll see more and more turbulence. And so they've designed, sort of by comparing this to simulations, a way to get an idea of what the structure of the turbulence is. But this kind of mechanism, and I'm just showing a schematic here, this kind of method completely ignores the concept of shape. And it doesn't allow us to use the data let's see if I can say this right. You know, when you look through those data with your eye, when we're scanning through those data cubes, you see certain kinds of features. And all of that information is thrown away. We can't really learn anything from this. We can only, you know, say, this is going to tell something about turbulence. We can't learn anything from the data a priori. This is a mixed slide for some reason. Okay, so now I'm going to tell you about my problems. So this is an image from work by Ford in 2010, which I just stole because it, I think, encapsulates this problem pretty well. So again, this is the galactic plane, and we're just looking in one particular slice in galactic longitude, just some particular area of the globe. This is a lower resolution telescope than the work with Arecibo, but what you can see is that there's all these sort of little blobby features. These little blobs. And these blobby features, in their observations, typically happen a little bit above and below the plane of the galaxy. Okay? And this is a really interesting area to study. The reason this area is interesting is because we know that the galaxy forms stars over time. And if those stars were to cease getting any fuel, you know, we wouldn't see any more star formation. But we see star formations, and we know that fuel has to be coming into the galaxy, and it really has to be coming in somehow. And so it's going to be coming in through the surface of this galaxy. This is called the disk halo interface, and it's sort of the wild west of the galaxy in a lot of ways because we really don't understand much about it. So probing these kinds of structures in the low halo of our galaxy, maybe a kiloparsec above the plane, may be a way to understand how fueling works, how material flows out of the galaxy, and what exactly is going on in this area of the galaxy, maybe an indicator for that. So we got interested in this problem of looking for these kinds of objects in our data at high resolution. So this is work by Mr. Saul that I'm involved with. And what we've done is taken our data cubes. So we have data cubes of this size, 150 of them or something, where we're going to search through for compact blob-like objects.
What's the scale?
The scale here, each pixel here is an arc minute. And our smallest resolution is about 3 arc minutes, about a milliradian. So 4 arc minutes. So what you're seeing here is just a particular slice in velocity, and then this line going through is just showing you what the spectrum looks like. So you can see these things poking up above the noise. Now, we wanted to drill down into this, and so we industrially devised a method of using basically a Mexican hat wavelet. In fact, 4 different Mexican hat wavelets in 3 dimensions. So remember, this is position, velocity space, moving this structure through these giant data cubes, looking for things sticking up. So once you do that, you can see you highlight some of these objects, and you have detections at 10, 20, 30, 40, 50 sigma. And that allows us to isolate individual structures or objects from this diffuse writhing mass of chaos that I showed you before. Then we basically do a water table analysis where we choose the brightest peaks and we grow them down, pretty standard methodology, and then we select out these objects. And then the objects that are small enough, we sort of consider as our isolated objects. So this is a program called BlobZoo, as an homage to Galaxy Zoo. And this was just run for us. We didn't publicize this at all because we only had 20,000 original objects or so. So we had a bunch of, each object was looked at by 3 people, and they were presented with this kind of display. We were able to navigate through these objects in position velocity space and look at their spectra and choose if they were good or glitch or connected here. Now, the glitch is a real problem because we have all this data that's contaminated in various ways because I don't do a terribly good job at actually selecting and getting rid of errors in the data. But this connected thing is actually really interesting, which brings us to kind of a complicated point, which is that, as I was saying before, I'm not terribly interested in objects. I'm interested in the structure of the thing as a whole. And it turns out these guys, they are somewhat isolated, but they also end up connected to larger structures. And that doesn't make them uninteresting, but it does mean that we don't really understand how to devise algorithms that are going to find what we're looking for because it's not completely clear what we're looking for. So there's a relationship, a constantly evolving conversation between the data and our algorithms as we go back and forth, trying to better understand where these structures come from and what they're connected to. This is what they look like on the sky in the end. This is our sky coverage. This is degrees in declination. This is hours in right ascension, and you can see every one of these little white points is one of the clouds that has passed all of our criteria. So again, this is trying to force an object-oriented paradigm onto a clearly diffuse problem, which has its ups and downs. This is a much harder problem, I think, and much more diffuse sky-oriented. This is work again by Naomi Griffiths, and what they found was looking in the plane of the galaxy. This is again the plane of the galaxy. There's all these striated features. You can see the grayscale here is again the neutral hydrogen, and there's these straight lines. And what they're seeing in the background, what they're showing with these straight lines, these things, is polarization of starlight. So polarization of starlight tells you that there's dust that's on magnetic fields that's polarizing the starlight. And so this is telling you by the correlation between these straight lines that you can just see with your eye and this stuff, that this stuff is tracing the magnetic field of the galaxy. So
Sorry, polarization is not proves positive that it's magnetic.
there.
Okay.
You'll agree that there's a correlation here. And so that this is tracing something about the structure. Doesn't have to be magnetism. Fair enough. So that's fascinating, because what it's telling you is that non-objects, this is a non-object, this is just some kind of diffuse feature that springs out to our eye, is telling you something physical about the universe. And so that means that we really need to track down these kinds of things. And if you look at our data, you see exactly the same things. It's just some random slice of data. As you paw through, you find these kinds of long, striated features. But how do you pull these kinds of things out when you're not looking for a particular object? And I certainly don't have my hands around the kind of technology to do that yet, which is sort of the reason I'm giving this talk, which is to say I don't understand how we're going to go through these vast, complex data sets that are confused by all sorts of backgrounds and pull out information about these kinds of structures.
You mean you want to characterize the structures? What do you mean by information? What are you looking for? You don't know what you're looking for. Is that what it is? So you want to characterize what kind of filamentary structures you find in here. But
Sure.
people that do large-scale structure like Voronoi tessellation already do stuff like that.
Yep.
Just-
Voronoi tessellation will go nowhere with this problem, but it's an example of a tool that will be helpful. Those are the kinds of tools I'm talking about.
Okay.
Absolutely. So this is what another slice looks like, and you can see, this is full of blobby filaments, and this is full of blobby filaments, but these are not the same blobby filaments
No.
very clearly to our eye.
Yeah.
But telling a piece of code that this is different than that that's a hard problem, at least to me. I hope it's not a hard problem to you. And then in the end, what we're really going to be able to do is compare a simulation. So people have been working really hard to build simulations of the diffuse interstellar medium that are magnetized, that have shocks, that have turbulence, that have all sorts of different physics in them, that hopefully have some kind of thermodynamics as well, and being able to compare to say, look, when we see these kinds of long filaments, they're magnetized, or if they're not magnetized, they're all shocks, whatever it is, and be able to compare that to this, I think is the future of this. And so to try to go through this, myself and Legsley and Destry and other students at Columbia and postdocs have been trying to learn more about machine vision, which may be an angle into trying to decompose all this. But I'd love to hear more about machine learning techniques, and I was thinking about maybe this could be a zoo project or what have you. I've been thinking all sorts of different ways to decompose this problem. Okay, so those are my problems. And then I want to tell you about the worst part of all of this. So this is the lab survey. It's about a few hundred by a few hundred resolution elements by about 1,000 channels. Okay. Now the Galphage 1 survey, which is what I've been talking about mostly, the stuff I did my thesis work on, is a few thousand by a few thousand, maybe 10,000 by a few thousand resolution elements by about 10,000 in channel space. Okay, so we've got 10,000 channels, 8,000 channels or so. I'm now working with a project called GasCap. So ASCAP is the poorly named Square Kilometre Array Pathfinder in Australia, the Australian Square Kilometre Array Pathfinder, and one of its projects is to survey neutral hydrogen in the galaxy. But it's even higher resolution. This thing is few tens of thousands resolution elements by about 16,000, 20,000 channels. Okay, and it's going to be taking data in a couple of years. And then the Square Kilometre Array, for which ASCAP is a pathfinder, is going to be yet another order of magnitude in resolution, and another factor of 2 in channel number. So this problem is just going to get worse as we learn more and more about this and as this flood of data continues. So I think understanding the diffuse universe in this way, and there are lots of other projects that are getting more and more data about the diffuse universe, I think is important and something maybe we're not yet prepared for. So thank you.
Mostly because I like to hear myself talk, I'd like to point out something. A lot of the talks we've heard today is about, I have all this data, what does it mean? You know, I got this temperature data, what does it mean for climate? I have this consumer data, what does it mean about their habits? This is different. This means I have all this garbage on a focal plane, what the hell is it? Okay, it's an entirely different problem. It's about data process, it's data reduction. You know, it's not even data process, data reduction. And if you go out and you build a $1 zillion system, you don't have a system until you figure this problem out. Okay? So I just want to point out the difference between these two problems and how important this one really is, because you can't solve any of the other problems that you talked about here until this one is solved.
Well, I can chime in about the zoos. One of the things we're definitely doing with the zoo projects, we're moving to computer vision solutions and looking at machine vision as a way of sort of tracking, you know, what the humans are seeing versus what the data is showing. So it's kind of problem. So I was really, I sort of really woke up in your talk when you talked about astroform. But anyway, but in that image that you showed where you had the bow shocks and these linear and curved features, that this is sort of what people are being asked to do in the Milky Way project, which is not called Milky Way, so you just doesn't if you're to find these bubbles, whether they're supernova bubbles or whatever. And we see a problem there, which is recurring in our moon zoo, where we ask people to classify, to count and measure craters. There's sort of a user fatigue factor that's going on. So with galaxies, it was easy. You know, here's a galaxy, click, classify. Here's another galaxy, click, classify. With something like people looking at maps or images like this, you know, find everything in this image. People, you know, they don't know when to stop. Okay, so in our moon zoo, we have some crater fields where people just, you know, measure the two biggest craters with the two smallest, or some completely random fraction of the craters in the field. Okay? So if there's some way we can apply computer vision to the problem, that is, you know, sort of tracing arcs, tracing lines, tracing things which, for almost like image segmentation sort of problem, where you can sort of find the features and characterize them in some computer-friendly way to go into a database that you can now do analysis on. Let's try now to analyze all this stuff. So I think there's really some interesting corollaries of what you're saying, doing here, and what we're trying to do in these other projects. We really are gravitating to sort of this machine vision instead of machine set compass.
But you're mostly doing unsupervised learning, right? Like you don't know what you're looking for. So there might be a little in machine vision that would help you, but generally machine vision you give it labeled images. Say you find faces in an image or targets of interest.
When I say machine vision, I mean things like find gradient detection, edge detection, you know, things like that. You're not labeling what it is.
Right.
You're just finding.
So one of Louis Bonan, so you mentioned the ESP games, but that's just one of Louis Bonan's games for human computation. His website is called WAP, Games with a Purpose, and one of them, it is images, and you ask two users to like draw the edges around it or something. That something like that could be adapted, but there they know what they're looking for. You know, they're looking for cars or people.
Yeah, I mean, so in this problem, or maybe this problem, you know, I would know if a computer gave me an output that said, I have an intensity in a direction as a function of position on the sky. I would know personally how good that was when I'm looking at a problem where, you know, there's something that's pretty clear that I'm looking for. It's just sort of spread this all up. But again, you have fields like this where, yeah, it's not clear the question that I'm asking, and I certainly wouldn't want it to have the same result for this as it had for this.
But what you could do is clustering. You could have a huge database of images and then cluster them, and then later you as the scientist would take a few random images from each cluster and say, oh, these are gas spirals, or these are, you know, I'm speaking very non-technical, but whatever they are, whatever they look like.
So you're saying, showing, you know, a zoo type project where you show two images and you say, great, on a scale of 1 to 10, how similar they are.
Right.
And if it shows, you know, this guy, or it shows shows this guy and this guy, it'll say, oh, they're pretty similar. Whereas it would show this guy.
Oh, well, for that,
guy
you
maybe
don't
not.
even need humans. So there's clustering algorithms. So these are used, for example, for medical diagnoses. You can take a bunch of images of tumors and then cluster them and then get a doctor to look at the clusters to sort of determine, which ones are more similar, which ones are more malignant, or that sort of thing. So that you can do automatically without humans, but there's always a number of how many clusters, which is not very well known. You can do a hierarchical clustering, where at the top you have one cluster, and then at the bottom you have the number of images of the cluster, but then you can take a vertical slice at some level, say 6 clusters, and then maybe examine some points per cluster to figure out, what atmospheric, what astrological stuff it is. But even if you saw an image like
just
that,
one
I guess
comment, I guess, to someone
yeah.
who does computer vision and machine learning.
Right.
So it's not quite clear to me that, if you were to put this through some machine learning pipeline, so computer vision pipeline, you could get much out of it, because the images are so complex. And if it's not clear to you, as an expert domain, what's in there, it's going to be extremely difficult to sort of get anything meaningful.
Right, it's not a
computer vision
supervised learning
algorithm.
problem, but
Right.
you said it's sort of an unsupervised thing.
Right, so it's an unsupervised, so in that sense it's sort of quite difficult. But doing something like what you suggested, sort of having humans in the loop, and then having them judge similarity, and then based on this sort of high-level information, being able to feed it into machine learning algorithms and computer vision algorithms, and try to pull out of this sort of high-level similarity is maybe a way to go. And that sort of ties into this, galaxization.
I think you have too much resolution.
I completely agree.
No, but I'm being serious. I think you need to reduce the resolution, make more general statements about what you have, and then start increasing your resolution until, it could be that half of those twirly things, even though they look different, are exactly the same as some other twirly things. Just the wind is blowing, to the left instead of the right. So you go back to, you have to pull back.
But the problem is that, astrophysically, you're we had, due to low resolution, astronomers, when I was in school, we were taught about the three-phase interstellar medium, right? And the point of these new discoveries from these alpha maps are that whole picture was just bunk. there's essentially nothing real in that model we were talking about. Because the structure, is what's real, and none of these phases really.
It's inherently complex.
Yeah, but you can't do face recognition looking at pimples. There's a
Sure, but that's because you know about spaces. But
well, that's right. He doesn't know about this, so let him start big and work its way down.
But you have more than just the two-dimensional. You have the third dimension.
Yes.
So again,
Yeah.
in theory, if you can characterize the structures, maybe there's some correlation with the structure shape and the energy in that structure or something. That seems obvious. And again, that you can leverage that totally off of people who have done Voronoi tessellation of large-scale structure. They are very good at characterizing filamentary structure in all different scales. They can tell you what those are. And then you have an additional component. So you might be able to characterize all this stuff. You just run it through and see what comes out. And I don't think that's that difficult. And that from that vantage point, frankly.
Yes. I wanted to ask about these 10,000. Because I think you're scaring us with these images. You pick certain channels.
Yeah. Some are black.
And, well, I'm pleased to say I know nothing about your field, but I think I've ventured into many of these. There's probably not much.
No. No. You can certainly say that some pixels are noticed.
And you would think that however many
Thank you very much.